All right, everybody. I need to make a couple of videos about kind of some wrap up material. What happens if your distribution is not normal? So, we spent a lot of time talking about normal distributions or the normal curve, but what if it's not normal? Okay. Um, and the answer to that is basically, hey, if it's not normal, we do what we can to try to make it look normal. Okay, because the normal curve is so easy for us to work with, right? But sometimes we understand that it can't be normal, right? So there's lots of distributions. There's an F distribution, a Poisson distribution. My statistics teacher was Italian, and he always said it like that. It's a French name. It's named after a French guy named Poisson. So we're not going to deal with any of those. We are going to deal with the T distributions, and we're going to deal with chi-square distributions. And we're not going to go too terribly deep. If you wanted to take an advanced statistics course, then you could, of course, go in and see a lot more about these. This is just kind of to let you know things are out there, to let you know how things are dealt with, that kind of thing. So, what does this mean? Your distributions aren't always exactly normal. The distribution curve may not be normal. It may not look symmetric. Or it may not be as tall as the normal curve is, or it may be shorter than the normal curve or whatever. It may look kinda symmetric, but not be normal exactly. It might not be quite right, okay? So, the T distribution, the one we're gonna focus on right now, is whenever, the population's standard deviation isn't known. Okay. And actually I already gave kind of a little bit of a hint earlier in the semester. When the standard deviation for the population isn't known, what do we do? Okay. Hopefully, in your head, you're thinking, well, we spent all this time looking at sample distributions, right? We took sample sets and we did all kinds of sample statistics, and we found means and medians and modes and standard deviations, right, for our sample. So hopefully you're thinking, well, we what we would like to do, and you're right, is if you're thinking it, is we would like to use S, okay, for the sample standard deviation. I'm going to cheat and abbreviate to estimate or approximate sigma, which is the population's standard deviation. Okay, so that's really light. I'm sorry. Sigma, it's kind of like a 6 on its side. Okay, that's the population standard deviation. Okay, so we don't know the population standard deviation. We're just going to kind of approximate it by using the sample standard deviation. This happens, or this can happen. We can do this if we have 30 or more samples. Okay, so if our sample size is 30 or more, okay, and we were able to, whatever it was we were doing, average weight of the baby or whatever. If we were able to gather 30 or more pieces of data, okay, on this sample statistic that we're after, um, and the sample needs to be normally distributed. Okay. For whatever this particular data set is, right? So, like, if it was the average weight of the baby, we would assume that a random sample of 30 or more, simple random sample, right, of 30 or more data points on average weights of babies, that's pretty Oh, excuse me, probably pretty normally distributed because it's based off of people, right? Okay, so if all of these things are true, then we can use the sample standard deviation. Okay, and that's what we're going to do. Okay, what if your standard deviation isn't normal? Okay, well, there's lots of solutions, like I said, but the t distribution is one of our solutions. Just one. There's lots of different ways to deal with this. One solution, period. Okay, so if sample's really close to normal, then what we're gonna do is we're gonna do a little calculation. T equals x bar minus mu. I'll talk about what this is in a second. We should know it by now, but divided by s over the square root of n. Okay. So real quickly, let's make sure that we all know what we're doing. Our t value here is going to be x bar, so that's my sample average, minus mu, which is my population average, right? Over s is the sample standard deviation over the square root of n, and we know n is the number of data points that we took, right? So it's the number in my sample size. Okay. So, what are we looking at here, really? If we kind of examine here, we've done a little bit of this kind of thing before, right? How far is it's not quite the same as standard deviation where we're looking at the exact sample data point and seeing how far it is from the average. What we're saying here is, hey, you have your average for the sample. How far is that from your population's average? Okay. So how far apart are your samples mean or average and the populations mean or average? So that's what we're kind of trying to figure out. And then, of course, there's always some weird adjustment, right? So they divide by the standard deviation to see, they're just trying to really figure out how close we are. Divide by the square root of n. Okay, so there's just adjustment steps. So what we're going to have is, whenever we deal with this t distribution, we're going to have something that they call the critical values for your t distribution. And those are the things we're going to be looking at. And these critical values, they're going to they're going to designate them as t with a subscript of c. Okay. So let's think about some stuff we need to be looking at. There's lots of properties for the t distribution. Things like your mean, median, mode need to be zero. It needs to be bell shaped and mostly symmetric um, around the average. So things like that need to be happening. But what it means, okay? So what does that mean? Being bell shaped. So it could kind of look like this, where here is my average. But see, it's not exactly bell-shaped, right? So maybe I've got just it's mostly symmetric looking. It looks bell-shaped, mostly symmetric around the mean, but it's not exact, right? Okay, now you've seen Dr. Webster drawing these things for a while now, and you know that I can draw them very badly. All the time. The idea here, the mean, median, mode are going to be zero. That means that they're right in the middle and you've got positives and negatives, right, on both sides. The other thing, and this was something we looked at whenever we were doing normal distributions, is that the total area under the curve, it's 100% or a 1, right? Okay. And remember, we got into probabilities, distribution probabilities, all that kind of stuff where we figured out, hey, probability is a 1, the total area is 100% or a 1. So all that stuff is going to kind of play together in this whenever we get here. So we're looking at now the inferential statistics where people need to make some inferences, right? Early in the semester, we were just doing descriptive statistics, right? We were just talking about, is it qualitative, is it quantitative, things like that. But now we're trying to say, hey, you have a data set and you need to figure something out about it. You need to infer something from the data set. Okay, so that's what we're looking at. Um, the book that I've been using for this class says that the tails on the T distribution are thicker. Okay. The tails are thicker is what it says. And I'm going to show you a picture of what they mean by this than the normal distribution is. So if I can find the page, I'm sorry. I thought I had it marked. I know I had it marked, but it got away from me somehow. Okay. So here we go with a picture. Okay. And if you can read this, this baby blue one is the tall, skinny one. That's the standard normal distribution. Okay. And then it says, and I'm going to talk about degrees of freedom for a minute, but if you have 5 degrees of freedom, you're really close to this sample distribution or the normal distribution. But if you have 2, it's a little bit fatter or a little bit flatter. Okay. And what they mean by the tails are thicker is right here on the standard stinker here. Right here on the standard deviation, look how close to the axis that tail is. There's not much there. But whenever I had 5 degrees of freedom, it's a little bit thicker here. That's what they're saying, a little bit taller even. And when it's 2, it's a lot taller, right? Okay. So what they're saying is it's not going to go as tall in the middle normally, and it's going to kind of flatten out earlier so that it's not getting all the way down to the axis. Okay. That's what they mean by the tails are thicker. Okay. Now, what the heck are these degrees of freedom? Let's look at that. I'm sorry. This got moved when I stuck the book up underneath it. What are degrees of freedom? Okay, so basically what happens is if you have a really tiny data set, then each data piece that you have can have a significant impact on what's happening in your graph, right? In your curve. So in other words, we know if most of my data is kind of pooled together right here in the middle, but then I have one piece of data that's way out there. That one piece of data, if I only have you know, 30 data points, that one piece of data can really shift the mean. We've talked about that, right? It can move things over or whatever. Okay. So how many data points are and don't draw that picture. It's a horrible picture. Okay. So the question is how many data points could be impacting what's happening here? Okay. How many could be skewing your data or messing around with it, basically. That's what we're talking about. So whenever we look at degrees of freedom, we talk about we calculate it. Okay. So it's calculated as the number of data points minus 1. That's your degrees of freedom. DF is how we're going to abbreviate that. Everything's got an abbreviation in this class, right? Okay. So you're going to look at it and you're going to go, oh, there's not much to that sample size. Oh, excuse me. I think some of the examples we're going to work in a little bit, you're going to go, oh, that's only 22 data points. We said we needed 30 or more data points, right? So if it's only 22, then we're probably really one data point is going to mess with us. Okay. And then one more thing. So the degrees of freedom need to be there. We're going to calculate them every time we do this. And then one more thing about these T distributions is that your standard deviation of the T distribution is going to vary with the sample size. Okay. So your standard deviation can change a lot with the sample size. Okay. And so what we're going to see here is our S is going to be greater than 1 for sure. Okay. So whenever we're looking at the sample standard deviation, that's what that S is, right? That it's for sure greater than 1. So these are not little bitty sample standard deviations. That's what I'm telling you. Okay. And what we just saw with that picture was that as the degrees of freedom increase, your t distribution gets closer and closer to a normal distribution. Okay, let's think about that. Okay, all of these things are happening as we're looking at this. Before we even start messing with the t distribution, this is what's happening, and these should be some of the things that we're looking at. So, what does that mean? Degrees of freedom increase whenever the number of data points increase, right? So, let's say that I have 12 data points. Well, that 12 data points, n minus 1 would be 12 minus 1, that's 11. That's a decent amount of data point or degrees of freedom. But what if I had 30 data points? Okay. If I had 30 data points, my n minus 1 degrees of freedom, n minus 1 degrees of freedom would be 30 minus 1 is 29. So which one of those two um, data sets, let me write it down. Data sets. 12 points, 30 points. Okay. Well, here are my degrees of freedom. I just did this, but I want to, in my head, but I want to make sure. 12 minus 1 is 11. That's n minus 1. Here, my degrees of freedom is 30 minus 1, or 29. Okay. Which one of those is bigger? 29, right? So this is going to be closer to a normal curve. Let's think about why that happens. Okay. Because we know that the more data points I have, it's like whenever we did probability and we did more trials, right? The greater the number of trials, law of large numbers tells us we're getting closer and closer to the probability, right? The theoretical probability. So here, same thing's happening. As I get more and more data points, I'm more likely to see a nice, pretty normal curve coming in, right? It's less likely to be skewed or whatever, one direction or the other. Okay, so that's what they're saying here. As the degrees of freedom increase, the t distribution approaches a normal curve, okay, or normal distribution. All right. So let's do some examples and see what this looks like. I know it can be a little confusing and I apologize, but we're going to do this one and then we're going to do chi-squared. And then that's the end of the kind of new material for us. So we're going to get this knocked out and be done. Okay, and it does require looking at a couple of tables. If you need those for a test, I will put them on the test, but at this point in time, I'm not planning to put the tables on the test. I would probably ask more of a theoretical question, a conceptual question to say, hey, do you know what's going on? Okay, so um, find the critical values of t. And I haven't finished telling you what those T sub C's are. Find the critical value, I will in a second, of T. Um, when you have a 95% confidence interval, and a sample size of 15. Okay. Now we said we need 30 or more to do this. So this is a really tiny data set. We understand that there's going to be a little bit of difference here, right? Okay. So what the heck are these T sub C's, these critical values, and what do they mean for me? Okay. So imagine, if you will, again, we have this curve instead of a nice, pretty standard curve. It's normal. It's pretty close to normal. It's symmetric. Okay. You got something going on in here. But it's not exactly a normal curve. It's close, but it's not exact. So what the heck's going to happen in here? Well, in the middle, it's a two tail, and that you can do it with one tail, but I'm going to stick with two tail the way we've been doing. Okay. And so what we're saying is we want to figure out, hey, kind of here's my X bar. We're looking at confidence intervals, right? We've done this. We know how this goes. And in the middle here, this center part, what we're saying is what? How much of my data can be explained away by looking right here in this confidence interval in the center? 95%, right? That's what we're hoping we have. If it was normal, for sure it would be, right? But we've got our errors and things like that. So what we're looking for here is we're looking for a T sub C and a negative T sub C, and I'll talk to you about that in a second. And these guys are going to be like the fences, the top end and the bottom end of my confidence interval for the T distribution. Okay. Now, why is this a T sub C and this is a negative T sub C? Well, I mentioned earlier that my mean, median, and mode need to be 0, right? Okay, I said that way at the beginning of talking about D distributions. So if this is 0, then I've got positive guys going up here and I've got negative guys going down there. Okay, so I need to find this T sub C, which is a critical value, and I need to figure out what that is. But before I do it, let's think for just a second. If this is my C, my confidence interval is 0.95, right? That's what it looks like as a decimal. Okay, 0.95 or 95%. Okay, if this is 0.95, what's in each of these? Think about the two tail. 95% here, that must be 5% here, right? So this part down here is going to be what? 0.025 or 2.5%? And this part here, same thing, 2.5%, right? All right. So that's going to come in importance for me in just a second, because I need to know what the heck's going on. The nice thing is about the T distribution that this is indeed kind of symmetric for me. So it's looking like I've got a critical value for T and a negative critical value for T. So those will be pretty easy for me to find. Once I find one, I have both of them. But I do need to know, I took that 5% that wasn't in the middle and I split it up, right? It's a two tail. So I've got 2.5% here, 2.5% there, and the data point here, or the decimal point here, that number is 0.025. And it's important for me because I have to use a table for this. And when I get to using the table, I need that number right there. Okay, so let's take a look. Okay, so here's what's going on. Oh, did we do degrees of freedom? I'm sorry. We did not do degrees of freedom. Let us do that real fast. My sample size with an E is 15. Then the degrees of freedom is n minus 1 or 15 minus 1, which is 14, right? Everybody agree? Okay, so I'm looking at a 95% confidence interval, 14 degrees of freedom, and I'm on these two tails right here, the 2.5%. So again, this is what it looks like in the textbook. Okay, you're probably not going to have to deal with this. You might have to deal with a normal standard deviation, but for these, we're not going to deal with them. Okay, um, we've got the C confidence interval, which we said was 95%. And we see here what it looks like. There's a t-value up here. There's a negative t-value down here. So what I need to do is figure out, okay, which one of these confidence intervals, again, it was 95%. So look right here. Level of confidence, C. Is it 80%? No. 90%? No. 0.95. That's where I was, right? And as I go down, I got one tail would just be this 0.025, right? No, nothing. But here for two tails, I've got the 0.05, which is it's a 5%, right? And let me come back here one more time. Degrees of freedom was 14. So let me come down here. Here's the 14, follow it over, and there is my number 2.145. Okay. So that's my T sub C, my T value, okay, and it's 2.145. T sub C equals 2.145, okay. So if that's the positive one, then we just make it negative, and my negative T sub C is negative 2.145, okay. And what's going on over here? Okay. These are the numbers beyond which, okay, um, I'll be at my 95%. So if you want to kind of interpret it, you would say something like this. 95% of the area of this curve lies between the negative 2.145 guy, he's the lower fence, and the positive 2.145 guy. Okay. So 95% of this data falls in there. All right. So I want you to do one because it's not necessarily obvious, okay? And you got to have a little bit of practice with it. So I'm going to give you an example, and then what I'm going to do is I'll ask you to pause it and make sure you have your example written down. And then I'm going to put the book up here because, again, I know you guys don't really have the book. So some of you might, but most of you don't. So here's your example. It says, find the critical values for a t distribution with a confidence level at 90%. So it's a little bit different. And a sample size of n equals 22. Okay. N equals 22. So it's a little bit different for to do a confidence interval, right? We'll talk about that in a second. But at first I need to figure out what my T sub C's are, right? My critical values. So what I'd like for you to do is I'd like for you to make sure you have this written down and you're aware of it. You're good to go. And then I'm going to put the page up here. So pause if you need to make sure you got it. Okay. I'm assuming you have it. So I'm going to put my book up here. Again, you can pause it if you need to. Level of confidence is right here, 90%. And follow it down and figure out what you got. And then find both of your T sub C's. Pause if you need to. Okay, do you have it? All right, let's talk it through. All right. First thing you should have done, hopefully, is you should have found your degrees of freedom. Degrees of freedom is n minus 1 or 22 minus 1, which is 21. Does everybody agree with that? I hope you do. Okay. So if you're at 21, then we look here at the 90% that I had up here. And you come all the way down to 21 and you get 1.721. Okay. And hopefully you have to do the degrees of freedom because sometimes I forget about them and I'll come all the way down to 22 because that's the sample size and I'll give 1.717. But hopefully you hear subtract a 1 in your head, and you only do 21 here. So 1.721. Okay. So if we were looking at this guy, okay, my mean, median, mode are right here at 0. T sub c is 1.721. And hopefully you figured out this guy back here is negative T sub c is negative 1.721. Hope you did all that while you had me paused. All right. I think that's it for T distributions. I just wanted to see how they go together. I'm going to stop this video and I'm going to do a separate video on chi-square just because I want you to see it all go together. Okay, so it's a different kind of distribution. I've got different pictures for it, and we'll move on from there. All right. Give me just a minute. Thanks.